So I just wanted to make a couple of comments on the project. That when you label a point, for example, the first point that you looked at, the y-intercept, which was number 4, I believe. First of all, when you label a point that sits on a graph, you have to put parentheses. So most of you had this. This was the value of the y-intercept from the model. The model being that the line that you were supposed to graph looked like this. It was given to you. So the y-intercept is when x is 0, y is this constant right here. The actual data value, I think, was 3362. That was the actual data point. This is what we call the estimated data point, or the fitted point. It's fit to the graph based on this model. Whenever you are asked to explain what a point means, given the situation, you have to look at what the units are for each of those and what the story is behind it. How is the x-axis defined and how is the y-axis defined? So both of these numbers, or language that talks about both of these numbers, needs to be in your explanation, and the units need to be attached. There's lots of different ways to explain something like this. One way would be to say, we know that 0 represents the number of years after 2000. So 0 means in the year 2000. So what this is saying, what this point represents is in 2000, we estimate, because remember, it's not the actual value. Some of you said will be or was. It's not the actual value. We estimate the average cost of tuition and fees at blah, blah, blah to be $3,129. Okay, so a couple of keys here. You've got your units. The unit is implied here with the year 2000. You see how each one of these numbers gets represented in your sentence. And whenever you're talking about using a model, you can use the word estimate or predict. Like when you went beyond the data set and you were trying to figure out when it was going to be $10,000, I think that point was something like this, right? If I remember correctly. So does that look familiar to people? So here you could have said, well, we're thinking that in the year somewhere between 2017 and 2018, we're predicting that the cost for tuition and fees at 4-year, the average cost of tuition and fees will be blah, blah, blah. Okay, so it's pretty critical that you represent not only the units, but somewhere in your sentence you see the values of both of your coordinates. Okay. Any questions on that? Because you'll be asked to do this on your first test. And I want to make sure, I mean, if you've had 096 here recently, you've had lots of practice with this. But if you placement tested and you probably don't have practice with this. Does anybody have any questions about this before we go on? Okay. All right. So we're going to start with this first problem here. Now, section 1.6, we're taking over a couple of days because they do lots of different equations, and I want to give you time to sort of absorb these new equations that you're looking at and sort of get the hang of it rather than shoving everything into one lecture. So we're going to only do part of the equations that they talk about in section 1.6. So start us off here. Kai, you want to start us off reading number 1? Okay. Okay, do you know why we call it a 4th degree polynomial, Kai? X to the 4th. X to the exponent 4 is the highest exponent throughout the equation. So that's what helps us to categorize it and call it a fourth degree. Okay, so see here that we have equations called polynomial equations. That's the big category, polynomial. And under polynomial equations, so some people you say this is the umbrella term. That's sort of the language. You can have a linear equation, which is the same as a first degree, and it has this form. Okay. You could have a quadratic equation, which has this form. So in this case, we say a does not equal 0, and in this case, we say a does not equal 0. Okay. And then today, we're going to look at equations that have degrees bigger than 1 or 2, bigger than the first or second degree. So the one we're looking at right now is called it's called polynomial, but we don't have a special name for it. Okay, we don't have a special name. We just put it under this umbrella term called polynomials. So you see an equation like this and you say, holy cow, I've never solved an equation with something to the fourth power in it. Is there anything I know from the previous work I've done? Well, one of the strategies we use with quadratic equations is getting everything to one side and setting it equal to 0. This idea of setting an equation equal to 0 is really important because when we set an equation equal to 0 and we can factor it, then we know how to solve it. Okay? So the first thing we want to do is we want to set the equation equal to 0 by moving all non-zero terms to one side of the equation. So to do that, we're going to subtract 6x squared from both sides. So let's do that. I'm going to subtract 6x squared from both sides. So we get x to the fourth plus x to the third minus 6x squared equals 0. Okay? So that's the first step. And again, it still doesn't look familiar to you as anything you've done. We're on class 9, Di. You got to keep going, okay? All right, so here's the first thing, the first caution. And let's highlight this here. You never divide both sides, in this case, by x squared. In fact, you would never divide both sides of an equation by x to any power. Does anybody know why we wouldn't divide by x squared? Kieran? So if you square root something, okay. What if, well, why don't we hang on to this question and see in a minute why, all right? We'll just hang on to this because sometimes these questions might ask you to like think a little bit beyond where you are and maybe you can't quite see it yet. So we'll come back and look at that. Okay, so right now, this left-hand side is an addition and subtraction problem. Okay, the left-hand side of this equation is a trinomial. It has 3 terms, x to the fourth, x to the third, and minus 6x squared. We can't use our zero product principle because this is not a multiplication problem. That's what product means. So right now, we have no help here. So in order to use the zero product principle, which says if you multiply 2 things and get 0, we know something about each of these quantities. Each has to be 0 individually, or they can both be 0. So right now our job is to factor this. Well, this isn't a typical factoring problem like x squared plus 5x plus 6. This is where you need to factor this using a technique that we almost always forget about. Does anybody know how we're going to factor this? Greatest common factor, absolutely. This is a lifesaver. When I teach 096, I literally tell my students to put it on their palms and on their back of their hands when we're factoring because it can get you out of a lot of trouble. At first you look at it and you say, I have no idea how to factor this. But once you use the greatest common factor, it becomes a little clearer. So what is the greatest common factor to the expression on the left-hand side? x squared, okay? And what we have left here is x squared plus 1x minus 6 equals 0. Whoo, you say, that looks a little bit better. So we need to make sure we have factored this completely. Okay, we've done the first form of factoring, which is pulling out the greatest common factor. And I can't factor x squared anymore. I could call it x times x, but that doesn't do anything. That's the same as x squared. So now you have to ask, is this second factor here, is this completely factored, or can I factor it one more time? Okay, and do you know how to do that, Di? 2 and a 3, what else? Yeah, one's plus and one's minus. So where do I put the plus and where do I put them? Okay, so if I do x, so look at here, we got a, okay, x plus 2. Let's get my little eraser out here. All right. Now you look at each individual factor and you say, each one is prime. So in this case, my zero product principal is going to look like this. Times c equals 0, because I have 3 factors. I have x squared, that's like the big fat A up here, that's like x squared. X minus 2 is like the b, and x plus 3 is like the c. So now my job to solve this equation is to say, when will each of those factors equal 0? Again, I want to point out that I solved this equation with another equation. If you go from either one of these equations to the other without putting equals 0, it's not correct. You solve an equation with another equivalent equation with another equivalent equation. Now you set each factor equal to 0. So we take this first factor and we set it equal to 0. There's really no work to be done because the only number we can square to get 0 is x equals 0. Okay. What about this one? We set that one equal to 0. You can, most of you just do that in your head. What's x going to equal here? 2. And then this one we set equal to 0 as well. And what do we get for our negative 3? Always check your solutions in the original equation. I'm not going to bother. I did this correctly, and you know. So how do you write this for my math lab? How do you line that up in the solution set? You put your smallest number first, negative 3, then 0, then 2. Right. Okay. So now let's take a look at why we don't divide both sides by x squared. One of the reasons. What is x equal? What is one of the solutions? X equals 0. So what does x squared equal? 0. So what happens if I divide both sides of this by x squared? What am I dividing by? 0. We can't divide by 0. The other thing that you would do if you were to divide both sides of this equation, let's take another look at it. Let's throw another page in here. So what is it? X to the 4th plus x cubed minus 6x squared equals 0. Okay. Let's go back to something here. This is a little bit, we won't be getting to this idea for maybe 5 weeks, 4 weeks, 3 weeks, I don't know, somewhere when we get to polynomial functions. But if I asked you how many solutions this has, you would say 1, 2, 3 right now. But see, this one comes from x squared, so we count it twice. It's what we call a repeated solution. So this really has 4 solutions, and notice that our original equation has a degree of 4. So you should be expecting up to 4, a maximum of 4. Sometimes one of them can be repeated, like this 0 is repeated because it's x squared. So we call that a repeated 0. So we have 3 distinct answers. If we had divided this by x squared at the very beginning, if you divide both sides by x squared, everything on both sides by x squared, including the 0, you still get 0 on the right side, but what you now get is x squared plus x minus 6. So not only are you dividing by 0, but to solve this, you're only going to get 2 solutions because you've taken a 4th degree equation and you've made it a 2nd degree. So you have the potential of losing a solution or more than one solution, and you get into trouble by dividing by 0. So never divide both sides of a polynomial equation by x, x squared, x cubed, or anything like that. Okay. Do you have a question, Brendan? Okay. Looked like you were getting ready to ask. Okay. All right. So our goal is to take whatever polynomial equation we're given and try to turn it into the simplest possible equation. In this case, the simplest possible equation was the product of initially of two quadratic expressions, and then we factored everything, and then we set each one equal to 0. So this is a linear equation, this is a linear, and this is a little baby quadratic. Okay, so we're just trying to get them down to very simple equations. Any questions on the idea behind solving polynomial equations? All right. So let's see what else we've got here. So here's another one. So how about if I'm the writer and you tell me, oh, this is the solving with your graphing calculator. All right. So we want to set the equation equal to 0, just like we did before. X cubed minus 4x. Well, let's put it in descending order. So we're going to have x cubed plus x squared, because that would be the next highest power, minus 4x plus 4 equals 0. So I'm going to enter this equation. I don't know the solution to this, and you can't guess by looking at it. Even if you try to 0, you'd get 0 on the left and 4 on the right. That's not going to work. So you can see now how this is just another method of how your graphing calculator can solve this. For example, let's clear everything up. Yeah? Oh, yes, absolutely. What did I write? Oh, yes, definitely minus 4. Thank you. Okay, so let's put this equation into, notice, we're going to put this equation into y1. This expression goes into y1 and becomes the first equation. This becomes y2, but I don't have to bother writing it because where on our calculator is y, whether we call it y2, y1, or anything, what is that y2 equals 0? How do you graph y equals 0? See, x, well, the values would be the x-intercept. What is y equals 0? It's a straight line, yes. Which line is it? The x-axis, right? So this is like saying, okay, I'm going to put this into y1, and there's no need to say y2 is equal to 0 because that is our x-axis. So remember before when we were using our calculator, when we had an equation like this, one approach would be call x cubed plus x squared y1, call 4x plus 4 y2, and see where the two lines intersect. That was the first method we used. This method involves the same idea, but now we're saying, where does this intersect the x-axis? And that's what we call our x-intercepts. So we entered this equation into y1, this expression, x cubed plus x squared minus 4x minus 4, okay? And I'm just going to do my normal window. And I can see now that what I'm asking is, when does this equal 0? When does it intersect my x-axis? Because I'm not graphing, you can think of it as graphing two individual expressions, each expression. It's just that 0, y equals 0, is the x-axis. So the solution here is, for what value of x is my y equal to 0? And that's what you traditionally call your x-intercepts. So let's see how we find the x-intercepts here. So let's copy this graph. I'm going to have to call it up again. Let's copy it. Take a little picture. And you can copy it right onto your sheet, onto your lecture notes. Okay. Now, visually, knowing what the value of, knowing that we use the standard axis, we know, the standard window, that this is negative 10, this is positive 10, this is negative 10, this is positive 10. And we know each of the increments here is by 1. So it looks like we can tell just from looking at this graph what our solutions to this equation is by finding these x-intercepts. There's negative 2 comma 0, there's negative 1 comma 0, and that looks like 2 comma 0. All right, so we're okay because it looks like it's really nice x-intercepts, but we're not always this lucky that it goes directly through one of the integers on our x-axis. So that's why there's a special button on our calculator that will help us find these values. So to find the values of the x-intercept, those values of x represents the solution to this equation. And since this equation is set equal to 0, the special button under second calc is the 0 button. And later on, you're going to be learning that as the name for x-intercepts when we study functions. So right now you say, what values of x makes this particular equation equal to 0? So you hit that, and the only thing now, you can play around with the cursor, or you can just say, let me find a number that is to the left of my very first intercept. It looks like my first intercept's around negative 2. So I'm just going to plug in a number like negative 3, right here, negative 3. Where's a number to the right? Now you got to be a little careful because you don't want to go so far to the right that you've gone past this next x-intercept. So right here, you say, okay, it looks like one is at negative 1, one is at negative 2. So I'm just going to pick a number a little bit to the right of negative 2. And you can put anything there for your right bound. So let's say it's, let's start this again. I didn't realize I had already hit the enter buttons. Here we go. So the left bound, I'm going to say negative 3. My right bound, I'm going to say negative 1.8, because that's between the two values. I could pick anything I want, negative 1.8. Then the next thing is going to have me guess, and you know we always hit enter when it says guess. And there's my first x-intercept, but that's the value of x. That's a solution to this original equation. So you can always check by going back to the original equation, which looks like this. So one of our solutions is x equals negative 2. We can see that, but again, we're not always going to be able to see it. So you put negative 2 back into the original equation, and you just want to make sure that everything you put in your calculator is correct. So you get negative 8 plus 4 on this side equals negative 8 plus 4 on that side. So the left side equals the right side. You're all set. And then you just play this game with each of these zeros. You do this 2 more times. Another way to do it is look at your table. If you've got a nice integer value like this, your table should show you. So you do second table set. Let's say we're going to start at negative 10, because that's where the x-axis starts, and we're going to increment by 1. So now you hit second graph, which is your table button, and you go down until you find 0. Let's see, am I lucky to have a nice, there we go. Negative 2 is one of the solutions, negative 1 is one of the solutions, and 2 is one of the solutions. Yep. Yeah. Yeah. Sure. Absolutely. So let's put that table here. Okay. We'll put the table right down here somewhere. We'll make it little, so we can squeeze everything in. So Karen, if I wanted to find a specific, like put a specific number in for x on my calculator, then okay, instead of telling it to, so x is your independent variable, we call that. Instead of telling the table to automatically start calculating all the y values starting here, you're going to go over here and say, I don't want, whoops, not there. I don't want you to do anything automatically. I want you to ask me what value of s. So you just hit ask there. And then when you come to your table, now you can put in any value of x you want. So let's try 2, because that looks like the other x-intercept. But it could be 2.0009. So let's just say x is 2. What's y? 0. Okay. So that's how you verify. All right. So this method is a little bit different than the method we learned before, because the method we learned before would have said, take the left side, call it y1, take the right side, call it y2, and see where those two intersect. But it gives you exactly the same answers. It's two different ways to find the same exact answer. Okay. Now, sometimes one of these ways will be more helpful than the other, and that's just going to come later on. You'll decide, do I want to set the whole equation equal to 0 and find the x-intercepts, or do I want to set the expression on each side of my equation equal and find where they intersect? But you'll get exactly the same answers. So let's look at how this, putting these two in, give you exactly the same answer. What kind of graph will I get when I graph 4x plus 4? A straight line. How many answers did I get up here for x? How many x-intercepts did I have? 3. So this line should intersect this graph in how many places? 3. And this is called, well, you can see what that's going to look like. You may not know off the top of your head what x cubed plus x squared looks like. So let's try it that way. So I'm going to put x cubed plus x squared in for one of my equations. So let's just delete out this. And then 4x plus 4 is going to go into y2, just so you can see how the methods differ a little bit in terms of the thinking, but they bring you to the same place. I'm going to say zoom 6 again, because I know everything's in my standard window. So there's x cubed plus x squared. That's this curve right here. And here's my straight line. Okay, the problem is I can't see very well where it intersects everything. So I've got to mess around with my window a little bit. I don't really need all these negative integers out here. And I certainly don't need all these positive integers out here. So I'm going to just adjust my window a little bit. I'm going to say like -5 to 5. Whoops. Come on, baby. All right. -5. And I'm going to go up to 5. I'm going to increment by like maybe a half now instead of 1. And what's happening? Let's see what error I'm making here. Oh, what did I put in there before? Oh, I didn't put a number in there. Let's say I actually got to go up a little higher on my y max to see my upper intersection. So I'm going to make this 20. So I've got to play with this a little bit, and let's see what I get now for a graph. Okay, I can see that curve a little bit better, and I can see that it goes through. It's a little hard, but it goes through here once, twice, 3 times. Okay. Now to find those points, you don't hit the 0 button. Remember, that's where we do second calc, and you say, tell me where these intersect. Okay. You got to do your first curve, your second curve, blah, blah, blah. So it's a little bit different. And that's what we did the other day. So again, you're not going to be asked to do this at any point. What you'll be given if you have any questions on homework is they'll give you the actual screen or the table, and they'll ask you, what does this mean? Okay, on your homework. Your answer actually, who's asking that, Karen? Your answer here, Karen, is I'm just going to hit enter, enter, enter. And that's my first intersection point, x equals -1, y is 0. So what you're finding here is you're finding the solution, which is the value of x. So when you're done, it says, what are the x values of the intersection? So your x values will be -1, -2, and +2. Okay, so you're finding the solutions to the equation. So you're finding the solutions for x. Andre? Do you still have any, is your little stat plot on? See, go like this, do second y equals, and look here, are any of these plots turned on? Okay, turn it off, and that's why you're getting invalid dimension. Okay, all right. All right, so you can solve some of these polynomial equations with your graphing calculator, with GeoGebra, because sometimes you can't do it algebraically. That's the moral of the story. Okay. All right. Radical equations. Radicals. Okay. I think radical equations are sort of they stick right out at you because you'll see a radical. It could be a square root, a cube root, a fourth root, whatever. Okay. So when we try to solve a radical equations, we use a little different strategy. We begin to solve an equation. We want to get all of our x terms on one side of the equation, usually, right? That's how it starts off. That's usually what we want to do. However, we've got sort of two terms here on the left side. Each of them have an x in them. Okay, so you say, well, which one do I get to one side and which side do I isolate? So you say, okay, I'm dealing with a radical equation here. So you want to isolate the radical, right? And that's pretty much what we do in society. We try to get rid of all those radicals, isolate them. We don't want them, telling, anybody go to the climate march yesterday in New York? If you read about it, grandmothers went, little kids went, ordinary citizens. Some people's political thing would call those people radicals, okay? So it doesn't, it's always a different perspective in society who a radical is. In mathematics, hopefully, no problems. You see the radical, keep it on one side of the equation. So what are we going to do to both sides here? What are we going to, minus the x, right? So we're going to isolate that square root of x. We want to get it all alone on one side of the equation. So we're going to subtract x from both sides. That's the very first thing I do. So now we have square root of x equals 12 minus x. Now, and again, I keep saying this over and over. I hope you don't get tired of hearing me say this. Anytime you have more than one term, put it in parentheses. Okay. Now, our job, we don't want an answer that says what the square root of x is. We want an answer that says what x is. So we have to undo what's happened to x here. Okay, what does this symbol actually ask you to find? This symbol right here. A little more specific, like on Jeopardy. No, the second square root, but it's even more specific. How many square roots does a number have? No. Yes. Except for which number? 0. So, no? Can you tell me any more about the root it's asking for here? Nope, it's not asking for plus or minus. How do I know that it's not asking for plus or minus? Can't hear you. I agree, square root, it's definitely a square root of x, but you need another thing right in front of here. Is it the negative square root? This is the negative square root of x. First square root. Does anybody know what this symbol actually represents? Or the positive square root. So when you see that symbol, it represents the positive square root of x. Because x could have two square roots. If x were the number 4, then it has two square roots, 2 and negative 2. So this is asking for the positive square root. So to undo the square root, you perform its inverse operation, which is to what? How do you undo square rooting something? You square it. Now this is where you'll see in the end why we have to be a little careful, because once we square this thing, we square both sides. That's why you have to have that second side in parentheses, because you got to square the whole thing, 12 minus x. When you square this and you do this sort of thing, you're right back to x. So this may sound like a lot of math teacher talk, but now when you look at x, you have x has no sign on it. This could be a positive number or a negative number. But back here, we wanted x to be positive. So you'll see in the end why we have to be careful and always check our solutions, okay? So we've sort of made a square root into something, well, I won't say that. All right, so how do I square 12 minus x? 144 plus x squared, right? What do you mean no? Don't I just square 12 and square x? 144 plus x squared, right? Oh, multiply it out. So what will it be when I multiply it out? 144, and then double this. If you multiply that, you get negative 12x, double it, and then what else? Plus x squared. Okay. What kind of equation is that? Quadratic. So we have a quadratic. We know how to solve a quadratic. We set the entire thing equal to 0, so we're going to subtract x from both sides. And I don't know about you, but I always like looking at these things in descending order of my power. So I'm just going to switch my terms around, which I'm allowed to do. X squared and 144, so it looks a little bit like what I'm used to. Yep, because I subtracted x from both sides. Okay, Di? That gives me minus 25x. Thank you for asking. Okay, now let's see. Can we factor it? And if we can set each factor equal to 0. So our goal here is, are there two numbers that I multiply to get 144 and they add up to 25? So let's see. Over on the side of your paper, you could do this sort of thing, 1 and 144. Does 2 divide into it? Does 2 divide into it? Yeah, how much? 72. Well, this adds up to 145, so that's not going to work. This adds up to what? 74. That's not going to work. Does 3 divide into it? Do you know the little trick for how to decide if something is divisible by 3? Add up the digits. 1 plus 4 plus 4. What number do you get? 9. Is 9 divisible by 3? That means 144 is divisible by 3. 3 goes into that how many times, Andre? Did you tell me a minute ago? 48. 3 and 48. That doesn't give us 25. That's not going to work. So what other numbers do we know can possibly go in here? How about, does 4 go into 48? Does 6 go into 48? Does 16 go into 48? You can keep trying. 4, 5 doesn't go in. You know, whatever 4's partner is. How about 9? Does 9 go in? Yep, 9 goes in how many times? 16. 16 and 9 add up to 25. Okay, so I can factor it. X minus 6, x minus 9. And my two solutions now, at least I think my two solutions are 6 and 9. Oh, thank you, 16. Thank you. So I would do this in my math lab, and you would get the wrong answer back. You'd get whatever it tells you when you're not correct. And the reason is right here. You have to check your solutions in the original equation way, way back before you squared, you moved anything. So let's go back to the original equation, and let's check each one of these answers. So we had x plus the square root of x equaled 12. Is that right? Is that the original? So let's check each one. 16 plus the square root of 16 equals 12. 16 plus 4 does not equal 12. So 16 doesn't work. What about 9? 9 plus the square root of 9. Does that equal 12? That's what we're trying to figure out. 9 plus 3 equals 12. 12 equals 12. You're a happy camper. Okay. So what you did by squaring both sides is you introduced an extra answer. We call this an extraneous solution. That's the kind of mathematical term for it. Anytime you have a radical equation and you square both sides, raise both sides to the fourth power, whatever you're doing, you always have the potential of getting an extra answer. So That's why it's mandatory that you check. I know you don't like checking, but with radical equations, you have to check. Okay. Any questions on this, on the procedure, what we did? Yep, Karen? Yep, the only answer here is 9, right? So we would take this out of here, and that would be my answer. Solution is 9. Solution set has 9 in it, and that's it. Okay, that's it. Any, yeah? That's one way of looking at it, yeah. Anything else before we move on? Okay, so let's see if we have, do we have anything else coming up here? Oh, yeah. Oh, baby, rational equations, exponents, equations with rational exponents. So I want to read this for us, Trevor.
Remember that all expressions of rational exponents can be written as therefore every equation exponent could be turned into a radical equation. However, I'm not sure you are thrilled with solving radical equations, so let's learn a new strategy for solving rational exponents.
Actually, it's supposed to be exponents. That's a typo. Cross that out and put exponents in there. Okay. So, solve the equation 3 times x to the 3/4 minus 6 equals 0. Where do I begin? Does anybody know that song? I'm really dating myself. So, one choice you have, of course, is to do this. What root am I taking here? What root is 3, the 4th root? I can do this kind of thing. You can change it to a radical equation. All right, so let's just do this as a radical equation because I know some of you will want to do it as a radical equation. So I'm going to put in, if I solve this as a radical equation, what was the first step in our strategy? Isolate the radicals. So what do I have to do to both sides to get my radical term all by itself? Let's add 6, right? Okay. Now I have this, 3 times blah, blah, blah. This whole thing equals 6. Have I isolated my radical term? Because what does it mean to isolate? It means you have 1 as your coefficient. So now what would I have to do? Divide it both sides by 3, right? So now I'm up here. The 4th root of x cubed equals 2. All right. So what root do I have to undo? What root do I have to undo? The 4th root, I have to undo the 4th root. What would be the inverse operation of the 4th root? Not multiply both sides. I can't hear. Raise it both sides to the 4th power, right? So if I raise both sides to the 4th power, those two undo each other, and I got x cubed on the left and 16 on the right. Whew, I'm almost done. Now how do I get x? How do we get x? Cube root both sides. So x equals the cubed root of 16. And that's your answer. Can't be simplified. That's the exact answer. So if I ask you for exact solutions and no estimations or whatever, you leave it just like that. If I say round it to the nearest hundredth, you throw it in your calculator and you see what you get. Okay? So that's what you would do if you made it into a radical equation. Let me show you another way. So don't let the itty bitty exponents scare you. Just pretend it's 3x minus 6 equals 0. So if we're pretending, our first step, we just did it, would be to add 6 to both sides. If we just look at that and say that's really not much different than 3x minus 6 equals 0. So I'm going to get 3x equals 6. My second step, to the 3/4. So if I'm looking at that and it says 3x equals 6, I know my second step would be to divide both sides by 3. And that gives me x to the 3/4 equals 2. Okay, so now here's where, your fantasy disappears because it really isn't x equals 2. It's x to the 3/4 equals 2. So here's where the new idea comes in. We want to get an equation that looks like this. X really to the first power, that's what we want. X to the first power equals some number. So does anybody have any idea of what I can raise this side to and this side to so that I get an x instead of an x to the 3/4? 4/3, right? Because when we raise a power to a power, we multiply our two powers. So I want the number 1, which means I raise it to the reciprocal of 3/4, which is 4/3. Because 3/4 times 4/3 gives me 12/12, which is 1. Yay, you're happy. So now you get x on this side equals 2 to the 4/3. And that's the same thing as the cubed root of 16, so you can leave it just like it is. So it just depends. Do you want to turn it into a radical equation and solve it using the strategy we looked at in the original equation, or do you want to keep it as a rational exponent right here and just work with your multiplication properties? Either way, you get exactly the same thing. Any questions on that? Okay, now I think I've given you quite a few problems to work on in your group or by yourself, however you prefer. I would suggest that you try to identify each one of these. Is it a polynomial equation? Is it a radical equation? Is it an equation with a rational exponent? So that you know which of the 3 strategies we just looked at works, okay? So any questions, just put up your flags. I'll come over and help you.